Great, good morning everybody. My name is Bob Freeman. I see some familiar faces in the audience. This is gonna be a bit of a repeat for you guys, so thanks for coming in anyhow. But extra practice, there you go, that's a good way to put it. My name is Bob Freeman. I am the research computing facilitator at the Fast Research Computing Group. I'm here today to welcome you to Odyssey, our premier research cluster. You guys are going to be using this for your class over the next number of weeks. I want to, before I actually start into the lecture and the walkthrough, I'd like to know how many people have used a cluster before this class? So some of you, okay, so that's great. How many of you feel pretty comfortable with Unix? Oh, so about half of you. Okay, so that's good to know. And how many people have used our cluster before this class? Okay, so a few of you. Okay, cool. That's actually pretty good. It's been interesting for me. I started my position here about a year ago. My background is in biology, and I've actually learned how to use clusters over the last 10 years with research I've been doing over at Harvard Medical School. It's been interesting for me. I've just a little background. I've actually trained so far about 500 people on how to use our cluster in the last year alone, which to me is actually kind of staggering. But each class, I see that the number of people who have cluster experience before it keeps increasing, and I think that's fantastic. Why this is actually a special treat for me is I'm actually on a 2-year grant from the NSF. My job is to help people take advantage of clusters, and if you're already using a cluster, to make better use of it or more efficient use of it. So it's a treat for me to be able to welcome you to our cluster. Odyssey is a 60,000 core cluster. We have 1,000 nodes. It's the biggest cluster in the New England area, and the size of it starts to rival actually a lot of the work that's done on a number of the Exceed resources that are the supercomputers around the country. So this is a great opportunity for you guys. My purpose here today is to actually help you get on board the HPC train very easily. And this guide that we're going to go through is a combination of lecture and some very minor hands-on, but I want you guys to try things out as we go through this. I hope all of you have already logged into the cluster. If you haven't by now or haven't been able to get in, we probably won't be able to help you this morning, so I would just say, fasten your seatbelt and enjoy the ride. With that being said, let's go ahead and get started, okay? But the goals here, as I already talked about, and I'm gonna skip through some of these slides. This is a condensed half hour, 20 minutes to half hour with hands-on, but we really want you to be able to use our cluster efficiently, excuse me, and to get your results faster. And most importantly, especially for the new time folks, we want you to be able to use the resources here without negatively affecting the other users on the cluster. We have, in a given month, 2 million jobs that are dispatched. So every single second, a new analysis is actually dispatched across the cluster for research. And because we do encompass research at Faculty of Arts and Sciences, School of Engineering, and Harvard School of Public Health, as well as some people at the business school, the scope of the work that we support is actually pretty broad. And so we'd really like you to be a part of that community, but it does require playing in the sandbox well with others. So that's what this is all about today. But really, in the end, we want you to be successful. It's great that you guys have this opportunity, and I hope that you guys take great advantage of it. Okay, so today we're going to go through this specific workflow from login all the way through the file systems, transferring files, to submitting jobs. And I'm briefly going to touch on some post-lecture help and resources for you to take advantage of. Okay. So our premier resource is the cluster. For those of you who are new to clusters, what exactly is a cluster? In our situation, and in most, ours is a little unique, but it's a tightly interconnected machine or series of machines that have identical hardware. And the hardware actually is very similar to what you have on your desktop or laptop, but oftentimes more components than usual. There's several special high-powered machines that have a special purpose, which I'll talk about. as well as large amounts of shared storage, and which I'll also go over. We also use particular software for managing the cluster. We use Active Directory to manage users and groups. That way you get to work in your area and people can't impinge on your work. As well as Slurm, our scheduler, which I'll talk a little bit about later on, but essentially Slurm is responsible for listening to your job and resource requests and trying to schedule the work on the cluster for you. As well as Linux OS, a Linux OS variant, CentOS 6, which is a variant of Red Hat Linux. Let me actually stop for a moment. I almost forgot to introduce my colleague, Plamen Krostov, in the back corner here. He's working with me for a lot of the work that we're doing with education and outreach. He actually has a background in theoretical physics and working with a lot of high-end compute, parallel programming, MPI as well. So he'll be supporting me with a lot of the work that I do here and moving forward. Sorry about that, Plamen. So again, this is a general overview of what a cluster looks like. The one thing that I do want to say what's different about Odyssey's been in existence for about 8 years and has grown organically, and I'll talk about this in the next slides. But the hardware tends to be a little more heterogeneous than one would expect, which does cause some slight differences for running jobs, especially if you're trying to run in a particular profile or usage pattern. And so that's something for you to keep in mind as you actually move forward with your work. It's possible that for the work that you're doing with the GPU programming, that this is less of an issue. But if you continue on with your research and do special research projects, this would be something that you'd want to take into account. So as I alluded to, this is a shared system. You have company, and I'll describe that. So some key definitions. The typical hardware unit is a node. And the nodes have distinct names which are indicative of locations and functions. When you first log in, you'll be on an RC login with some number. This is the login node, and it's a gateway to the whole cluster. But this node is actually less powerful than all the compute nodes, which is one of the reasons why we ask you not to do any computations on the login nodes. And then another one that you may see is holy to a blah, 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 blah. And these are actual compute nodes that we tend to try to name them in some particular vein. Holy only happens to be the fact that these are in Holyoke, Massachusetts. Okay? The basic computational unit in a cluster is a CPU core. So each core runs on average one job. Okay? Most compute nodes, especially in the general pool, have 64 cores arranged on 4 CPUs. So each compute node runs 64 jobs. And this is the first indication that you will be sharing compute nodes and the resources on that node with the other jobs. So a typical compute node has 64 cores, 256 gigs of RAM, or on average you have 4 gigs of RAM for your job. There are 2 network cards. One is an InfiniBand or an IB card. This is a high-speed card that interconnects all the computers with storage inside a particular data center, as well as a gigabit Ethernet connection for communication outside of the data center. And then also there is a small local hard disk arranged on each of the compute nodes that you use for boot up and scratch work. Okay? So the thing to remember is that all the cores on the node, and hence all the jobs, share these resources: the memory memory usage, the network bandwidth, et cetera. And so again, this is why it's important that as you start to do your work on the cluster, that you ask for appropriate resources so that you don't potentially negatively affect anybody else. We've done a better job over the last year since I've been here in trying to keep you inside of your own little sandbox, if you will, what we call C groups, for those that are familiar with Linux. But there are still other ways that you could potentially cause problems with other jobs. It's relatively minor, but again, we have to make you aware of it. Okay? And feel free, if you have any questions, feel free to stop and ask. Okay? So what is Odyssey? Odyssey is actually, as I said, it's grown organically. It's in 3 different locations. We have lab storage and logins here on campus. In Downtown Crossing at 1 Summer Street, we have lab storage, home storage, 2 of our different types of login nodes, as well as a lot of the older private nodes that PIs can purchase, and that becomes their priority compute. And then out in Holyoke, Mass, about 100 miles away, you have most of Odyssey in our Massachusetts Green High Performance Computing Center. This is actually a green LEED certified data center. That's a consortium from 5 universities here in Massachusetts. In addition to the rest of the compute that's there, our Regal compute storage is there, and I'll actually talk about that. So the topology here may affect some of the work that you do, and this would be particularly important if you're trying to do work on login nodes, but you're accessing compute out in Regal. So for instance, we typically say it's okay on login nodes that you copy files, move files, etc. However, if you're actually working with files primarily on Regal, and you're trying to make copies, and your files are large, it's probably something you won't want to do, because if you think about it, you're on a login node, you're on Regal, copies work by moving data from storage to RAM back to storage. So you'll be basically copying from Regal to Boston back to Regal, which is really not what you want to do. So in those sorts of instances, you want to make sure that you have the ability to get a compute node, and once you have a compute node, you're inside the same data center with the storage, and so the copies will go much faster. So you have to think about the topology of the system as well as the operations that you're trying to do and adjust your work appropriately so that you do this in the most efficient way possible. Yes?
Does it take forever to get a compute node, like just to copy something? Isn't that like completely impractical?
So the question was, does it take forever to get a compute node just to do a copy? You can, and I'll talk about this when we talk about the partitions, if you try to get a general compute node, depending on your resource request, it could take up to a day. Yeah, but if you're doing something like, if you're just doing interactive work, we recommend you use Interact or Serial Requeue, and those actually will dispatch within a matter of seconds. I think the longest lately I've had to wait is about like 30 seconds. Yeah. So, and we'll actually live demo this as we do this. Okay. All right, so so the typical workflow we're going to go through here today, and we'll do this a little bit of this hands-on, is logging in, uploading files, interactive sessions, so that you can actually work with compute nodes. You load the appropriate software. You test your script or program interactively to make sure it works okay. Once you have it working, then you actually would want to submit it as a batch job, so it runs in the background, and you can keep doing work that you want to do in the foreground. Once that works successfully and there are no problems, then you can start to scale up to your work. Are they going to be doing any scaling on Odyssey? Not. Okay. Not a lot. Okay. So I won't talk about that as much. But as you may work with future projects, this is something that you want to do very carefully. And again, how jobs run on singles may run very differently than how they run in tens and hundreds, because core count, disk placement, file access, all these things start to matter. Okay? So most of you already know, you use your RC credentials for these actions, and to log into Odyssey, we do have two-factor authentication as a hard external shell, but once you're inside our system, then it's pretty easy to move around. Your account will lock automatically if you fail 5 login attempts, so just know that you can get up, go get a cup of coffee or walk your dog or something, and once you come back, your account should be unlocked. Okay? And again, if you're switching labs or if you're going to be doing work on Odyssey beyond this, let us know if you are changing your lab affiliations, because the user and group management stuff will matter. And I do have to say that your account credentials should not be shared. It's a violation of Harvard University's security policy for you to share your username and password with anybody, so please do not do that. Okay? Okay, we do recommend that on Mac or Linux you use Terminal, and for PCs that you use PuTTY. You can use other programs, but if you have problems, we won't be able to support you when you send in help requests. If you want to do X11, which is a GUI-based login, we do recommend Xquartz on Macs or Xming on a PC. When you log in, you'll do an SSH terminal session with your RC username at this address. And if you want to use X11 forwarding, you'll actually want to include a -y and C in uppercase. This will enable compression and also X11 forwarding so that all the GUI commands are sent through. Okay. So I'm actually just going to go ahead and part of the live demo. You'll have to get the laugh with me. Oh, shoot. Okay. So love it when it does this. Let's see if I can get it right. Nope. Okay. So let's do this then. There we go. All right.
Uh-oh.
You guys can barely see my code down there, but okay. So the login is actually pretty straightforward. We do give you actually just a login banner. I'm one of the people that controls the little message of the day down there, so you may see this change from time to time. We're actually trying to help make this be a little bit more informative for each of you so that it actually is more useful. If I wanted to do X11 forwarding, and let's try that. If I do SSH-YC, bfreeman at login.rc.fast.harvard.edu, and I'm going to do xquartz, X11, there we go. So you'll notice I've actually got X11 running here right now. I could log in this window if I wanted to, but I like doing this typical black terminal sessions. So let's see if I can get this right. 982.821. And the easiest way to make sure that this is working properly is, if for your X11 session, is the easiest thing you can do is just say xclock and hit ampersand, and if everything goes okay, yes, I actually now have a GUI clock. So I can actually now run GUI programs from Odyssey on my laptop. Okay. All right. So let's put this back in. Okay. And we've already done this. We do expect you to have good Unix skills. There's a website on our page for 8 different bullet points. We ask you to make sure that you feel comfortable with those. That way, you actually can work pretty easily within our system. Okay. The GUI login I just mentioned, you can do X11 if you need to use something like MATLAB, RStudio, Lumerical, or COMPSCI, any of the engineering applications. X11 is okay for very minor amounts of stuff, but if it's very graphical intensive, we want you to do No Machine as a GUI session. And this is basically a remote desktop session. Just know that you need to use the VPN in order to do so, and you'll log in this manner. And these screenshots go from setting up your client to a particular port, and we have 2 GUI logins now, RCNX01 and Holy NX01. Once you get a desktop session, you'll get a terminal session. You'll run your terminals, and you'll get an interactive session, which we'll walk through. And then once you get a compute node, you can then load your software, and here it's RStudio. So it's pretty straightforward. Okay, any questions on this? Grand, okay. So for placing files, we do recommend FileZilla for all platforms. Do configure it according to our instructions, because the 2-factor authentication will get in the way if you're transferring files, especially large numbers of files. If you feel pretty Unix savvy, we do highly recommend SCP or rsync. Rsync will allow you to resume interrupted transfers, and will also copy just portions of files that have changed. So it's a great synchronization utility. You can also download things from the interweb by using curl or wget. For each of you, you guys have your own home folders, so you can actually mount your home folders on your desktop and laptop as a shared volume. Do follow our instructions here on how to do that. It's a little tricky first time you do it, but once you save that information, you can do it as much as you want to. And I have, for reference on here, some examples of how you can use SCP and rsync on wget to actually download some information. So I won't actually go through these. Do know that if you do start to use rsync, that this is a little tricky when you start to use your source specifier, that the final slash on this indicator here, their source, will make a difference whether you're copying a folder or copying the contents of a folder. So in the exercises that I've actually outlined for you on the website are some things that you can actually try. I'm not going to go through them here. It's not as informative as actually some of the other stuff that we'll do. So just know that these are there as a resource for you. Okay. For storage, this is kind of important. So storage on large systems like this are not like a hard disk on your desktop or laptop. The way that we do it is we actually bundle disks together to make a virtual volume. Once you actually have a volume, we then slice it up into what we call file systems. And you would access those file systems through a particular point on the file system tree. And here you might be able to guess that it's /n is where on Odyssey you would actually access all the different file systems. So what does this really mean for you in practicality? Okay, for some of you who are already here and already logged in, if you were to type the command, so I'm actually in my home folder, you can tell because I have the tilde at my login screen. So if I type df and a period, you'll actually get the specification of what your file system is. Well, I can probably tell you that everybody else here is not going to have rcadmin, but you're going to have some home and a number. And you'll notice if you turn and ask your neighbor next to you, you probably won't have the same one. These are the different file systems that we've divvied these disks up into. There's actually 300 people that have home folders on that same file system with you. So as you start to work, what you do will affect or could affect the 300 other people that are sharing these bundles of disks with you. And this is one of the reasons why we ask when you start to do your submitting jobs, it's okay to submit jobs 1, 2, maybe 5 or so. But as you start to go about 5 simultaneous jobs, we don't want you working out of your home folders, because if you do 5 jobs and you do 5 jobs and you do 5 jobs, suddenly these disks start to become tasked, and the performance will go down significantly. Because the input-output through the network card for these disks is at a finite level, and it's not optimized for large cluster work. So we'd want you to use one of the Scratch file systems. Okay? And just to show you, in addition to your home folders, there's also lab storage. And lab storage has exactly the same problems. It's great for small amounts of work, but for a large amount of work, not the best. Okay? So just to show you also, if you wanted to see, if you look at what else we have on Odyssey, we probably have, probably not the right command. We probably have about 200 file systems that people can access. So there we go. So you can see that we actually host storage for many, many different labs. And we make these available through this /n mount point. And that's how you would access any of the network storage. And that's what the N means. Okay? All right. Want to move on. This is a reference slide for you to know about the file systems. What I really want to talk about is using Scratch and Regal. Okay, so if you start to do large amounts of work, but it sounds like you're not going to, just know that there's storage on each of the compute nodes that you can take advantage of. It's a local hard disk that you have about 4 gigs of space that you can use, but in reality, it's underused, so you can use more. And you can use this slide as a reference because I do have a usage pattern here that you can go back and take advantage of if you're actually starting to do larger amounts of work. Okay? Yes?
If you're running a job on a lab partition,
Yep.
so Regal's really far away then, right?
Yes, Regal's out in Holyoke, yes.
Scratch is close.
What's that?
Is Scratch close there?
So Scratch is on each compute node. It's a separate hard disk that's unique to each compute node. The thing you need to be, again, this is sort of a consideration, is if you have stuff on your lab disks, those are here in Boston, but stuff on Regal is in Holyoke. And if you submit to Serial Requeue in general, you're probably going to end up out in Holyoke anyhow, because that's where most of Odyssey is located. So again, this is a situation where communication, especially for large amounts of data between a lab storage and out in Holyoke, Mass, is not very efficient. Okay. So you may want to think about parking most of your data, copying it over to Regal. Okay, and that actually leads me to my next slide, is Regal. Regal is our high-performance, highly parallelized file system that you can use for most of your compute. This is imagine, if you will, about 10 computers behind 10 banks of disks, and it's a mesh network. So any of these computers can access any of these disks. And the idea here is that as you start to scale your work, hundreds and thousands of jobs, all of these computers can listen to read-write requests and access any of the disks. So essentially, you have a compute farm that can serve storage for you. Okay. The nice thing about the Regal is, again, because it's static, you can place your files here in advance of your jobs, either by copying or using FileZilla. But because it is shared storage, we do clean the disks every month. So anything older than 90 days is wiped off. For you guys, since the class is only until the end of this year, probably not anything you need to worry about. What we do recommend, the usage pattern: place your files, run your job. As a part of your job, copy the data back from Regal to your home folder. Your home folder is 40 gigs. We don't touch it. And there's actually hourly snapshots as well. There's no backup on Regal. Okay? Great. You guys, not as important, but since you're not doing informatics work, but we do have public data sets here. I don't know, you guys, we may set up a folder for you guys to do all of your work on Regal. And I'll get that set up with Ray if need be. Okay. Any questions on the file systems? Great. Okay. So software. Now that you've actually logged in and placed your files, you need to do some work. What are you going to do? We have tons of software on Odyssey. Most of it's open source and non-commercial. We do have some restricted licensing. We don't make everything available. We use a module system called LMOD that you load incrementally the software that you want to use. And I'm actually going to demo that in just a moment. This is opt-in, so you'll explicitly have to take advantage of the LMOD system. We do recommend that you make it part of your normal routine. Okay? And what that looks like is the following. You would do this command, source new modules. This will opt you into the new system. If you want to then load software, you simply say module load in the software title. Okay? If you want to lock yourself into a specific version, you give the version number and our build code, and this way you can use the same version over and over again. If you want to know what we have, you can also use this command module spider and the package name, and that will actually get you access to whatever we actually have. Okay? So as an example, so I do a lot of bioinformatics. I'll show you what I already have as part of my login. So actually, I should show you my login. So my login script, I actually use the new modules already. If I can find it. There we go. So right here, source new modules.sh is a part of my bash login script. So every time I log in, I will actually be using the new module system. And I actually load some modules here. You can see that I'm loading some stuff specific for the admin group, but I do a lot of work in Perl, so I actually always load the Perl modules. That's all I load. You want to make sure that you load as little as possible to prevent problems with conflicts. If I look at what I'm actually running, you can say module list, and you can see, again, I'm using very little. Although I've done 2 loads, you'll see I actually have 4 things loaded here. And one of the things that's nice about LMOD is that if you use a package that requires other software, it will load those other software packages for you. And that's something that we set up. So as an example of why we do this, I do a lot of bioinformatics. One software package I want to use is Bowtie. So if I type Bowtie, command not found. So I can say module spider Bowtie, And it will tell me that there's actually at least 2 packages here, bowtie 1.0, bowtie 1.1, and other possible matches are in this CentOS branch. The CentOS branch is our old module system, and you can access that by using module load legacy. And once you do module load legacy, then you can also access all the other module sets, okay? And I'm really interested in only the latest.
Uh-oh.
So I'm going to say module load bowtie. Okay, once I've done that, then I can say module list. You'll see that I now also have bowtie loaded, which is the latest. And if I say bowtie, I now actually have access to the bowtie binary. So what happens behind the scene is that the module system will basically go out, load the latest version of the software, and adjust your compute environment, specifically modifying your environment path variable to include bowtie as a part of that, or whatever software that you're using. So for the exercise that we have for you, there are other environmental variables that may be set, such as your compiler linker, compiler flags, libraries, these sort of environment variables that allow the Unix system to actually run appropriately. Okay. So are there any questions? Yes? So to get the environment variables, you just say env. So, yeah. So this shows me, but if I want to see, there's 2 commands to look for software. One is module spider and the software name. The other one, which we tend not to use, is module. This can be useful. Module avail will show you all the different software packages that we have in the core. And the reason that this is in particular important is the reason why LMOD works so well is we basically put you down a path that may be compiler specific if we want to prevent conflicts of software. So core is anything you can access right off the bat. But if you need something that uses, for example, the easiest example is MPI. MPI is version and compiler specific. So you won't see that until you load a compiler, okay? And then the Ds indicate that this is the default version of the software. And in certain instances, the latest version won't be the default, and I think R and Python may be that way. We have Python 3 on there, but if you do a module load Python, you get module 2.7, because people haven't yet totally transitioned to Python 3. Okay?
Uh-oh.
All right, so let's go back here. All right, again, I mentioned module load legacy. If you're not using LMOD, you can still get stuff by saying module load the old version. Just make sure you use the new modules. And again, also, you can put source new modules in your bash RC, but pretty much you should put everything in your login script, in your Slurm script. One thing you have to be very careful of is if you do module loads manually and then you submit a job, that's carried over into your job. If you forget to do that at a later point in time, your job will fail because you hadn't manually loaded them and your job inherited your environment. So it's always best to put all of your module loads explicitly inside of your Slurm scripts to ensure that they run. You don't want to wait for a job to start running and then you actually get a module not available or software can't be found. So do put everything in your Slurm scripts, okay? The other thing I do want to tell you about is if you need software, especially Perl, Python, or R packages, you can set this up yourself. You can put these in your own home folder. For Python in particular, it's the Anaconda environment, and we have instructions on our website for you to be able to learn how to do that, and also update Python modules as well. Okay. All right, login and interactive. Now the real workhorse here. Okay, so when you log in, you go on one of the several login nodes. It's the gateway to the cluster, limited resources. Just do small amounts of work here, copies, moves, rsyncs, these sorts of things. But only CPU-intensive work should be done on the compute nodes. And so you have 2 options. You can either submit batch jobs or get interactive jobs. And there is a progression that we actually recommend that you use, and again, I outlined it. is as you start to do work, you want to actually get an interactive session to actually do things interactively, obviously. This will put you on a login node, and you can test things out, look at error messages, get direct feedback. And only when your software is working, then you should submit something to the background, to Slurm in the background. So this is the command that you would use to get an interactive session. It looks complex and obtuse. It's really not that bad, and let me show you why. And we'll do this as well. So, so there are basically 3 parts to this command, or any of the commands that you would use are typically the sbatch and srun. The first is whether you want to run something in the foreground, srun, or background, and you'd say sbatch. For these next 2 parameters are specifically for doing an interactive session, and you just sort of have to memorize them, but a way to keep them in mind is PTY is pseudo-terminal, and if you're doing X11 or GUI stuff, you need to say X11 first. The second part is actually the resources that you wish to get from Slurm, and there's really 3 main ones that you should think about. Memory, where you want to run your job, the partition, and the time. Okay, so mem, P for partition, T for time. These other 2 are optional if you're only asking for 1. This is the number of cores or CPUs that you want, and the number of nodes. If you're only asking for 1 core, you don't even need to include these 2. Okay. And then the last part here is actually what script or program that you want to run. And in our situation, since we want to get an interactive shell, we want to get a shell which we want to work with interactively in the foreground. We explicitly would say that we want a foreground bash session or bin bash. Okay. So let me just show you what that looks like, and feel free to follow along. So I have, let's see here. Okay, so what you would do is, again, srun. If I'm doing a terminal session, I need to do the --PTY. I'm not doing X11 forwarding. I don't need GUI stuff, so I'm going to leave that off. But if I wanted to actually get a GUI session, like run MATLAB, a GUI MATLAB or RStudio, or for that fact, if you want to do, you wouldn't do IPython notebooks that way, but yeah, skip the Python stuff. And then essentially now our resource requests. So we want an interactive session. So interactive sessions typically go on interact. I need the amount of time, and just for this class, I'm just going to say 30 minutes. If you need a longer amount of time, you can do it in days-hours.minutes format. And then the amount of memory that I want. And again, remember that you get on average 4 gigs of RAM, but because we're just doing something simple in the terminal, you can ask for as little as like 500 megabytes. Okay? If I wanted to get multiple cores here, if I was doing multi-core work in an interactive session, I could specify that, but I'm not going to. And again, this is optional. I only want 1 core on 1 compute node, and bin bash is the shell that I want. Okay? And then in a few moments here, we're actually going to get an interactive session. An interactive session is a job. It's a foreground real-time job. And you will see, I hope, in a moment that you will get allocating resources for a particular job ID. And you'll need to keep this in mind, okay? And that will be important in the next couple of slides. All right? So in the last 10 minutes, I'm just going to breeze through the things that you do need to know. Resources. How do you know? Choosing resources like attending a party. You really need to RSVP the number of guests that you want to bring. Okay? You really need to tell Slurm the amount of resources that you want to use. Okay, so if you bring extra guests, there's not enough food and drink, and the host will be probably kind of pissed that you showed up with lots of extra people. Slurm's kind of the same way. It will try to accommodate you. The problem is that all your jobs, if you go over disk usage and CPU usage, because you are restricted into a sandbox, your job will run slowly as you try to do more work with more CPUs that you're not really getting. But if you actually use more RAM or more time, your job will get killed because you've actually gone over your allotment. If you actually request a lot and bring too few, like RSVPing, again, the host is not going to be very happy because they've made a tremendous amount of effort for you to actually have this extra work or people, and you're basically wasting their time and resources. And it's the same way with a scheduler. If you've requested 8 CPUs or 40 gigs of RAM, we really want you to use it because no one else can use that but you, all right? And if you don't use it, you've wasted the resources. And also, if you ask for more than you really need, especially largely, your job is bigger and it becomes harder to schedule. So it's in your best interest to try and actually optimize the amount of resources you request. At the same time, you also want to make sure that, like any party, you don't show up, have a drink and eat, and then leave right away. The schedule is the same way. There's a lot of overhead in trying to schedule your job. Remember, one job every second. And 60,000 cores, 1,000 nodes, all sorts of RAM configurations, et cetera. It's a lot of work. So we really ask that you try to make sure that your jobs run at least 5 to 10 minutes in length. Sweet spot is anywhere from an hour or more, okay? So time, over ask, and then once you figure out how much time things take, because again, you're trying to run things interactively first, you'll actually have a good idea of how much time it takes. So then go back and ask for less. RAM, your software should tell you how much RAM you'd use, but again, if it doesn't, and a lot of them don't, then you really need to then figure this out on your own. One is, again, you get 4 gigs of RAM by default. So ask for 4 gigs, and then after your job is done, you can then lower that number, because if you need more, somebody has to give up their RAM so you can have more. And this command here, sact, will actually give you the amount of RAM that's used. The rec mem is what you request, and the max RSS is what you've actually used. And again, if you are in an interactive session, this is a job. So if you exit your interactive session, you can then use this command to figure out how much you've run, okay? This is a quick slide that, again, it can be a reference. I just want to mention, I will go through it quickly, but you can go back and look at this later on. Quickly, interact is where you get interactive sessions. Private compute, you guys will be using Holy Seed's GPU. This is an instance where you guys have access and other people don't because of your affiliation with this class. Oh, gig mem. It should be big mem. Sorry about that. Where for large amounts of RAM, again, restricted access in general is where you would run most of your compute that requires large numbers of nodes or large amounts of RAM or large numbers of cores. Serial requeue takes a little bit of explanation. Serial requeue is the most powerful queue or partition on our cluster because it hits every single compute node, every single core. We do recommend that you, if you're going to use this, if you're running single core jobs, you should submit here because things will get dispatched in a matter of seconds. But you can actually do up to 8 cores and maybe up to about 12 hours. But because this hits private nodes also, if you land on a private node and the node owner submits a job, your job could get killed and requeued automatically. So there are a few things that you can do to mitigate this to ensure that your jobs run okay, all right? It's not typical that you actually will see preemption, only when the cluster gets really, really busy. And actually, it's funny, I've actually seen it twice now within the last 2 days. It's really busy right now. So what you can do things to make sure that you can optimize how your jobs run so you're not recomputing stuff already done. But serial requeue is probably the best one for you to use for just small amounts of single core up to 7 days and small numbers of cores for small amounts of time. Okay, so submitting your job, very simple. You say sbatch 2 ways, the one-liner or a script. The one-liner looks a little complex, but it's sbatch, your command inside /wrap, and then all the resource requests as flags on the command line. And you've already done that with the srun, okay? With this, once you say sbatch and that once you do this and say sbatch, you get back a job ID. And this is your handle, if you will, to actually control that job. The options here are both required, recommended, and optional, and I'll go through that in just a moment. Okay, so if you don't want to use a single line, and that doesn't make sense if you have a lot of work to do, you then would basically make a script. A script is just a list of commands in a text file. And you want to then include some additional things in that text file that tell Slurm what you want for your job, okay? And you would then, again, just say sbatch and that file name. Now, I named mine .slurm so that I know that they're true submission scripts and not regular scripts, but you can name it whatever you want. Just stick with something and keep it that way. So I'm gonna go through really quickly 4 different templates you can use for the different types of jobs that you're gonna be running or potentially could run. And there are slight variances among them, and it's important that you understand these differences, okay? For single core jobs, it would look like this. You have 2 sections, your shebang line and your partition name, your module loads, and then your commands down at the bottom, okay? You could submit just that, and that's fine, but if you do that, you'll get defaults for memory and time, which is probably not what you want, okay? We do recommend, and if you want to modulate those parameters, you include the following options. Number of cores, number of nodes, time, memory, which is a pool of memory, and then output files. These output files are separate from output that your program may write to a file. But these are great because you need to capture messages that may relate to status from the scheduler itself. In particular, the E or error file would be error messages from your software. And if you do need help, we would ask you to submit your error logs, and that's what this E file is. And then the other one that we would suggest is also, if you're getting started, is including mail notifications. You can put your email address in here, or if you want a text message when your job is done, you can put the email address for your text messaging service as well. Okay. For multi-core work, there's actually going to be slight differences. Essentially, you're going to up the amount of memory that you would give it. For more cores, you would change the core count, and then you would pass along to your program the number of cores that you request through this P parameter. And this will vary from program to program. But what's important here is you get a variable, Slurm tasks, that tells you exactly what the value of that core count is when your job runs. Another type of multi-core work that you might do is OpenMP. And here you have to explicitly say export, and again, that to pass along the core count. And finally, if you're doing MPI work, things would change a little bit more. You can go over 64 cores, which is a typical compute node. You can also specify, you have to specify your memory as mem per CPU, because this may be spread across multiple nodes. And then you can also specify whether you want one node, multiple nodes, or if you leave that option out, Slurm will just basically schedule it on as many nodes as are convenient. And again, you would pass your core count along to your program with the Slurm end tasks variable. Okay. Once you've actually submitted your job, you have 3 important commands that will be your friend. Scancel will cancel your jobs. It will be your best friend, I guarantee you. In the 14 years I've been doing cluster work, I always make mistakes. I still do. And I regret having submitted a number of jobs, and I quickly run and do scancel with my username, and that will cancel every single job. Be careful. If you have an interactive session, that's a job also, so you'll kick yourself out of an interactive session. But just know that you can slice and dice this. SQ gives you info on currently running jobs, and saccount gives you historical information. Okay? And again, after you run jobs, you'd want to include this. All right? So there are common commands that you can have here. I just want to wrap up because we're just about out of time. There are advanced topics. Since this is a computing class, I would urge you to look through these. These are the mainstays of schedulers. As you start to scale your work, these things are important. Fair share, job dependencies, job arrays, and then how you can actually parallelize your work using the disk subsystems that we have on this scheduler, okay? There is a slide for problems and pitfalls. Take a look at it. And then getting help, just know you can go through our portal to submit tickets. The take-home message, if you remember these 5 things, you're golden. You'll be able to actually get through the cluster pretty easily. Just keep these in mind as you work through them. It's pretty straightforward, but if you can keep these in your mind as you work moving forward, you'll be pretty golden, okay? With that, I thank you for your attention. There is a slight or small homework assignment. What we're going to have you do is I've given you the framework for what you need to do. The slides here, and I didn't walk through an example of building a submission script, but again, you can see from the handout that you actually have 4 examples there. So your toy example or your toy exercise is to actually go in, log into Odyssey, and from this website, and I think it's on your chat, is it Piazza, is your minor assignment. And basically, what we want you to do is go through the test SH and the test PY. This will allow you to run a job taking advantage of the GPU on one of the compute nodes. The run test.sh is a very basic framework for the script. You need to go in and put in your sbatch directives, your module loads, and call your script appropriately. Include the mail notifications for yourself minimally so that you can see that you successfully submitted and run a job. And once you've done that, then actually email this to your TFs. Yes?
Actually, it looks like I was just trying to run it. I think there might be a misconfiguration in the opening CL.
Oh, is there? Okay. I actually ran it last night. It seemed to go okay. Okay. I know you actually have stuff in your okay. So just go ahead and actually fill out the proper directives, run it. If you get it completed successfully, forward that to your TF with the text pasted into your email message, and you're golden. All right? Any other questions? Yes?
If you load like a module like Python, will it automatically also load all the NumPy, SciPy, whatever?
We have this, it's a good question. You get the default if you load Python, our defaults, and we do have NumPy, SciPy there. We do recommend that you actually set up your own environments. That way you can modify it, but you should be getting, that's correct, Plowman. They get their own NumPy, SciPy, right, when they do Python? Yeah. You get our default environment, yes.
Okay.
Yeah. The only thing we probably won't have in there is if you're doing multi-processing or any multi-core work, because it's compiler specific, we may not have that in there. So is it in there? No, it's not. Okay, yeah. So there you would actually need to set up your own environment and pick a specific compiler. So, yes? Uh-huh. You canceled it? Oh, if you to cancel it, if you are doing an S run, an interactive session, you just say exit, and your job will end. Yeah. But again, if you need to cancel it, you can just say S cancel. So you can actually see here, I'm on a compute node now, and I'm out in Holyoke, Mass. So, and if I do SQ to look at my own jobs, this is a bash session running on an interactive node out in Holyoke, Mass. So, all right, cool. Thank you very much. Appreciate it. I'm sorry? It's on the Piazza. Cool. Thanks.